June 2nd, 2023. Reading about the differential analysis and integral analysis. Analysis is all of that, and dynamical modeling is basically all the world application. I have here another one of these university mathematical texts. I've collected as many of these as I could find. Here in the frontispiece of it, there's the general editors are Aitken and Rutherford, Daniel Rutherford, and determinants and matrices, statistical mathematics, the theory of ODEs, waves, electricity, projective geometry, integration, partial differentiation, real variable, infinite series, integration of ODEs, introduction to the theory of finite groups, German English mathematical vocabulary, analytical geometry of three dimensions, topology, functions of a complex variable, special relativity, volume and integral, vector methods, classical mechanics, fluid dynamics, special functions of mathematical physics and chemistry, tensor calculus, theory of equations. Now all they have of this are this theory of ODEs and waves, and this is waves here I'm looking at, real variables. I got the complex analysis, the topology, vector methods. So I'd started reading this book on waves, and we had left off yesterday about talking about waves on strings, or the plucked string, and that it radiates phonons, or sonons and phonons, as those being, discrete quantities, and what's otherwise a continuous milieu. That particle physics is really just a conceit to the idea of being able to deal with things in finite quantities, vis-a-vis the development that comes into and goes out to the continuous rates of change. To establish what are the continuous rates of change, the differential. That for something like the harmonic functions and all that goes into its role about the Laplacian, that the Laplacian is the sum of the second order differentiated partials, and when it's zero, it's the Laplacian. It's a harmonic function. And that's similarly with waves, about how they kind of have these things that define what is the displacement of the wave at any one time, vis-a-vis the tone that's emitted and the tones, the notes. It's something that a long time ago was one of the first things that was ever found to establish that a law of physics defined via a means of proportion and measure, that it could be figured out how to make stringed instruments that have certain notes only according to their measure. And it was quite a sensation. So the notions of waves is there's basically a notion of waves or blobs. So waves are a continuous and a continuously changing state of energy, and that also is reciprocating in a sense, or restitutive, oscillating, and vis-a-vis a blob, or the discrete, or the phonon, and acoustic, or what is the energy contained that so travels, is another way to look at things. And the lava lamp of the physics. The lava lamp is a pretty simple device, and what it is it's got a lamp, and at the bottom of the lamp is a heat source, and that happens to be a light, an incandescent light. And so the contents of this is a bottle, and inside the contents of this bottle are two liquids, and so one is just like an oil of some sort, and the other is clear, and the other one is some sort of waxy substance that is pretty much balanced about room temperature in terms of its material properties. And so what happens is the light, and so the substance, when it's cool, it naturally sinks. And so when the light source activates in the heat source, then it begins to collect heat radiates into it, and it changes that. Then it changes basically its density, or that otherwise it becomes via the way that it absorbs heat, with regards to that otherwise that it's more opaque, that then the blobs of the lava float to the top of the lava lamp, and then when they reach the top, then they cool off and then they fall back down. So it has this really nice cascading fountain and waterfall effect, which makes for, as it's just kind of a natural thing, that it's among similar types of desk toys or bric-a-brac of the dynamic sort. Kind of like one of those paintings that's got many different layers of sand and in it is oil otherwise, and maybe a bubble. And so when you turn it upside down, the different layers and layers and layers of sand, because they're of different densities and their graininess in the media, will, over time, one by one, fall off from where they've maintained according to basically a surface tension or a meniscus of sort within the layers, the layered media, that according to how this is designed, within a particularly flat enough plates and with a particular minimum distance between these plates, or maximum distance, I suppose, and a particular organization in the size of the grains of these various grains in the sand, and the contents of the oil and the amount of air in it, that when it's tipped over, it acts kind of like a liquid regulated hourglass. So the regular hourglass for the sands of time, as it were, it of course is just a shape that is restricted in the middle, so that sand will only fall through it at a very metered rate, and that sand, though it's a grainy material, basically acts as a liquid in that sense, because the way that it flows is in the way that we can think of something that otherwise would be a liquid, that it's as of drops, or as of a constant drip, or as of a stream. Then with the sand, that the sand as it flows and falls through the hourglass is similarly like so. So on the one hand, it helps reflect these notions of flow and fluxes and of particles and waves, or the continuous and discrete. That as well, then it gets into these other ideas of the dynamics of the situation, where the one is kind of a matter of the orientation that can be made in effect, turning the hourglass or the sand painting upside down, and that it begins a transition to its equilibrium again, which is just its own image in effect, because then it's just turned back over. It's just reversible. That then something like the lava lamp basically implements that in terms of the continuous flow of that up into the lava lamp and back down, as a sort of in this oscillative and oscillating and restitutive. And so these are kinds of things that catch the eye, because they help illustrate the facts of nature about it that make it kind of like so. Another one of the desk toys is when they have the ball bearing is a particularly uniform steel spherical ball, and so it's used in such things as wheel mounts, and where the idea of the ball bearing is that in a wheel mount between an axle and the wheel, you put in ball bearings, because then they roll around inside. And so while the wheel rolls, that the ball bearings roll, and thus usually packed with grease, then how it works out is that it provides a frictionless environment. And because they're very strong, then it works out that it's such a matter of, as a mechanical device, it's a cool thing. So anyways, besides that, that's their usual function, the ball bearing. And otherwise, you think of it like a pinball. It would be a similar thing, and some pinballs are just any ones alike, and they are all pretty much of a common size, but some are magnetizable, and variously there's all kinds of interesting effects and applications in the implementation of the pinball machine, or the pinball game, or the roller coaster, and these kinds of things, which always have been amusing, and people get into those things. So the ball bearing executive toy is that these are connected as hung from a frame the balls are in a line, and they hang as of a pendulum. According to that, they're each anchored in two spots, so that as they swing back and forth, those maintain essentially rigidity or extension, tautness, so that it only will swing back and forth in a line like a pendulum. And so, being that they are as a row of five usually, or one or two, or pretty much any number, you pick up one side and either side, and you let it go, and it hits the collected mass of them. And because of their basically good modeling of perfect inelastic reactions of collisions, then off the other side of this array, the other ones will fly up just as high as the other ones were dropped, or as with much force, or as with much inertia. That establishes a pendular motion, and it's restitutive and oscillating, and radiates over time by the click-clack of their sound, and the various other factors that are vanishing, that will finally come to rest in usually just kind of a slight swinging of the entire thing back and forth. Where otherwise, when that swinging won't happen until the very end, because when the first impulse happens, if you pick up two of the balls of the five and you drop them, and then they hit the main body, then what will happen is out of the other side, the two on the other side will fly up, and then according to gravity, fly back and hit that, and then it will reciprocate and proceed. But the center ball stays at rest. Yet finally, one of the states of the condition is that as it attenuates, gets down to the floor, finally, the entire array will be shifting back and forth a little bit. That's according to the resonance, that this is an example of a way to see kind of these factors that are otherwise like, you mean I have to consider how it goes to absolute zero to understand the attenuation and dissipation of heat in the kinetic? Well, it has that. Or do we really have to think about, the sound of the sea in the ocean, and it's been there forever, and you really do hear the ocean in the shell, or that it's otherwise just as a matter of, it's a matter of echo, and it's a matter of frequency, and it's a matter of resolution, and this kind of stuff. Well, it's the background, it's the floor. Do we really need the cosmic background radiation to look out and see that, it's about 3.7 degrees Kelvin, and that's also infrared and microwave, which is really surprises people because they thought it would just be light, but there's also heat throughout the universe. Oh, really? Well, yeah, it's a thing. It's not absolute zero, These get into kinds of things where it's very important to be able to frame things in the small, but still in the measurable, so that you can figure out experiments in the stopwatch that can basically show that these sorts of transitions can then have a model. They can have a model as a differential equation, and it's governed by time and configuration and experiment. Then the idea is that those are the same sorts of models for some other classical systems, and then about the supermodels basically get to where, well, in our turning over the layer of the sands in the sand pane timing and relayering glass, to figure out what would the properties be if each of the layers dropped at once, or held longer, or held indefinitely with regards to some other process. That becomes like super fluidity or super conductivity, or being frozen. That those are complementary things that add up in these models. Now, I've kind of gone into this as an idea about the waves and the differential equations, because then the idea is that to express those in terms of systems of functions and equations, and parameterized by time and the configuration of space, that it ends up pretty simple. These things are pretty comprehensive. So looking through the chapters of this book, There's for sound waves, there's and because there's basically waves in liquids, sound waves, electric waves, and general considerations: Doppler effect, beats, amplitude modulation, group velocity, motion of wave packets, Kirchhoff's solution of the equation of wave motion, Fresnel's principle, and diffraction at a pinhole. This is the camera obscura essay. Fraunhofer diffraction theory. Retarded potential theory. There's kind of the accelerated and the retarded, the potentials. That's a key thing, and it helps reflect a lot of what's going on with the electricity in the air, or when something stops, that it starts at rest, besides that it just falls immediately. The potential theory. That's the end of this introduction on waves. So these would be, if getting through all this other stuff, maybe they'd be approached. But of course, each of the sections has like the kinetic and potential energies for waves and liquids, the kinetic and potential energies for sound waves. And then in the electric waves, it's talked about the skin effect, which is kind of like the difference between the core effect, and internal reflection. And otherwise, electricity has a fluid model, but it has also differences, these superclassical analogs to the fluid model. But these are some of the kinds of things that I really enjoyed when I've been trying to figure out what goes into this formulaic parameterization of waves, and what numbers and constants and quantities, the quantities, end up helping define their descriptive and their qualitative aspects. The shape and the scale parameters, say, of a distribution as quantified, that also are qualia, or qualitative aspects in the descriptive about the dynamics, where, like in these plane curves, that, well, anything you can draw basically is a form or is a surface, and so it's just these level lines or whatever as would affect a topography, or as good as functions as anything else, for example. Then that with regards to linear systems, or otherwise, where those are on the other side of the inductive impasse, from where it's tractable, that it's only sensible as it's only sensible that in the conclusive that it's totally dissipated, it's off beneath the floor or beyond the floor, or it's only tractable as having deconstructed or rewritten these terms and these other terms. The idea is to figure out for these shape and scale parameters and these qualitative aspects of differences in their shapes, how it works out that they go together. So as a gotten book, we got into Clairaut and D'Alembert. And so here that's been reflecting a lot of talk about the identity dimension. Well, what's that? It's like, it's just kind of among the usual grab bag toolkit of identities and formulas, and of course the surrounds, the milieu, the vector space, the coordinate space, the setting of real numbers, and the setting of the infinite dimensional vector space, but particularly the xy plane, reducing that to the xy quadrant, and then being able to look at that as of analytical character and value, because, a lot because of root 2, and the fact that the length 1 along this axis has abscissae that are like 1 over root 2. And similarly, that the length of it that's root 2 has abscissae that are 1 and 1. And so, but otherwise, it's a lot like rewriting these formulas when they'd be just kind of scribbles as about something. They're kind of curled up in terms of this identity dimension, which is just the quadrant of the positive numbers in x and y, and that are often symmetrical about x and y, or otherwise reflected like so. That then it can be considered for a bunch of different things. And so that was discussed quite a bit in terms of the Clairaut and D'Alembert in one of the earlier talks about this thing. And it's been a E-Day fix about a singular solution in the linear fractional equation and Clairaut and D'Alembert. So, reading from this book, who is Colson, C. Colson, we should now obtain some special types of solution of the equation of wave motion. We shall then be able to apply them to specific problems in later chapters. We may divide our solutions into two main types, representing stationary and progressive waves. Now, there's been a lot of talk about the fashion of naming and the ubiquitous disambiguation of naming and things in mathematics. So it's also to be largely avoided any kind of political association or social association of names of objects in mathematics, which are neither good or bad, although you can talk about formulas and solutions being well behaved or poorly behaved or nasty or nice, or these other usual things that relate to expectations. That at the same time, when it says stationary and progressive, it just means, you know, not moving and advancing or accumulating and ... They're both what they are, not the non-logical part, say. So, we have already dealt with progressive waves in one dimension. The equation to be solved is d squared phi over dx squared equals 1 over c squared of d squared phi over dt squared. So this is very much as if after the Fourier setup, where it was reused the same kind of thing in terms of the getting x and t to equal each other in terms of the separation of terms and this kind of thing. And reading about D'Alembert and then it was talked about how the identity dimension sits in that as kind of a singular thing, and about how these things are going to be that it can make it so that curves can be drawn that fill out and have to be solutions of these things. Its most general solution may be obtained by a method due to D'Alembert. We change to new variables u equals x minus ct and v equals x plus ct. Then it is easily verified that d phi of dx transforms to d phi of du plus d phi of dv, and d phi of dt transforms to negative c d phi of du plus c of d phi of dv. D squared phi over dx squared becomes d squared phi of du squared plus 2 d squared phi over du dv plus d squared phi over dv squared, and finally d squared phi over dt squared becomes c squared times quantity d squared phi over du squared minus 2 d squared phi over du dv plus d squared phi over dv squared. Then that factors in terms of algebraically, it looks like x plus y, x minus y, where x is d squared phi over du squared, and y is, or rather that x is d squared phi over du, and y is d squared phi over dv, and it's a differential operator calculus. So when you say square and you implement it as a factor in algebraic, you rewrite it as a formula, end up with these terms that make for this kind of combined algebraic operator approach to differential calculus via operator calculus that looks like x plus y, x minus y as a form. When these changes are made, the equation becomes d squared phi over du dv equals 0. That becomes the solution to the progressive wave in one dimension. Now, when you're reading about the nonlinear electromechanical effects and applications in Mogan, and I'll look back to it, because this D'Alembert and this second partial derivative in respect to the Laplacian and a lot of these different kinds of things is used in a lot of different places in the analysis, where there's raising the order, integrating it up, and then taking it back down. And it's not just one, but two suffices for a lot of these things, because it makes up for what is kind of like an area to box it out into space and get it back down. that otherwise the D'Alembert and the Laplacian and the Lagrangian and the other things that have to do with the second order derivative all share a lot of common features. And so it's to be evaluated when we're talking about the nonlinear electromechanical effects and applications in Morgan that have things going on about the piezoelectric and what happens when there's a radiation according to one thing that ends up adding compensative or propensities and tendencies and terms to what would otherwise be vanishing things, or what would otherwise make it so that the nonlinear contributions are in effect as of otherwise where these linear contributions have vanishing nonlinear effects. And so the partials are not missing anything, the Laplacian or the D'Alemberts here. That the ideas of this algebraic approach in the operator calculus is to get it so that then there becomes these addition and indexing formulas about what ends up being the differential equation, so that it's not just that the term in here in the middle of this and the term in both the variables is 0, but that's just the singular solution of it. And so then what falls into that and what arrives at that, what systems of constructive waves that add up to that, arrive at that, makes so for more of a way to treat as an analytical basis than these wavelets, or otherwise for these zones, for these waves, how to arrive at via systems like a Fourier style analysis with an arbitrary, appropriate, complete set of functions and definitions and coefficients which add up to these things, to arrive at this, as the author put it, for this, example of a solution. The most general solution of this is phi equals f of u plus g of v, f and g being arbitrary functions. In the original variables, this is phi equals fx minus ct plus gx plus ct. The harmonic waves are special cases of this, in which f and g are cosine functions. The waves f and g travel with velocity c in opposite directions. So they travel in opposite directions, and they arrive at some point in time at the same point. In 2 dimensions, the equation of wave motion is so this is for the 2-dimensional case. And then in the 1-dimensional case, it was just d squared phi of dx squared, or the Laplacian in x of phi, the amplitude. So in the second, in 2 dimensions, it's just d squared phi over dx squared plus d squared phi over dy squared. Or that in the identity dimension, it's just 2 d squared phi dx squared. Oh, well, what does that mean? Is like, well, when we project it back down, this is all that's left of it. Okay. And I'm just kind of making this up as I go along, but that's just an example of it's a mathematical development being carried along, has been found to be appropriate in all these places, that in all the developments and derivations of all these standard methods of the differential analysis, it has its special place. That's how it goes. By a method similar to D'Alembert's, it can be shown that the most general solution involving only plane waves, and the author's footnote says, strictly these should be called line waves, since at any moment phi is constant along the lines Lx plus my equals const. Involving only plane waves is phi equals f of Lx plus my minus ct plus g Lx plus my plus ct. And so this L and M for x and y kind of become familiar as from the linear fractional equation in D'Alembert and so on, and Clairaut, Clairaut, Clairaut. Whereas before, f and g are arbitrary functions, and L squared plus m squared equals 1. where, for example, it's trivial when L or M is 0, you know, that the other one is 1. And it's just x plus ct and x minus ct. In 3 dimensions, the differential equation is the Laplacian equals 1 over c squared and d squared phi dt squared. And the most general solution involving only plane waves is, similarly with a parametric plane, Lx plus my plus nz, in which L squared plus m squared plus n squared equals 1. And this gets in then, well, what's the identity dimension in 3 dimensions? It's x equals y equals z. All right. What does that mean? Well, then what it would make is, if you can imagine 3 dimensions, and that makes, in 2 dimensions there are quadrants. Plus, 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 minus, 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 plus. And in 8 dimensions there are octants. And so then if you consider that, then it gets into the question of, look, well, how do you split the cubic octant according to its diagonal into realms that basically make a reflection about them? Well, it's totally non-trivial compared to the 2D case, because there's more than one way to do that. But the basic idea is of that, well, yeah, the function that's this identity dimension, or the identity function, is just extended to any number of variables for any number of dimensions, to be the identity dimension in the nth dimension. Then, though, with regards to these things that solve, for example, in the 1 dimension, well, it's just x equals x. Well, yeah, that doesn't help very much, but it, you know, cancels. And then for x equals y, it's kind of like so, and it'll be carried on like this, is that it's singular for a bunch of these different things. So it's amusing me quite thoroughly. Now, going on, the author says, now besides plane waves, he says, there are, however, other solutions of progressive type not involving plane waves. For suppose that we transform 20, which was the 3-dimensional differential equation, to spherical polar coordinates r, theta, psi. And his footnote says, see, for example, Rutherford. The equation of wave motion becomes d squared phi over dr squared plus 2 over r d phi over dr plus 1 over r squared sine theta d theta of quantity sine theta d phi d theta plus 1 over r squared sine squared theta times d squared phi over d psi squared equals 1 over c squared d squared phi over dt squared. If we are interested in solutions possessing spherical symmetry, i.e. independent of theta and psi, we shall have to solve the simpler equation d squared phi of dr squared plus 2 over r d phi over dr equals 1 over c squared d squared phi over dt squared. So this is because it has on the orders of r and r squared are involved in the differential equation, where it's not the Laplacian with everything second order, but it's first and second order in the radius about these spherical coordinates. So here what I'm interested in is the spherical coordinates in this identity dimension, because just like in the plane, the idea is that the quadrant split into octants, or 2, can then be kind of conformally mapped and expanded to the half plane. And so that in terms of polar coordinates, it's just like negating and doubling the polar coordinate. That's the way to transform the coordinates. Or adding an offset and making it negative. It's just a 1 or 2 step thing. To compute something like, when you compute the rotation matrix for a 90 degree or pi halves or a right angle turn or flip or what, there's a particular series of constants to multiply and not use sine or cosine, because often the numbers you'll be dealing with are not having that their products in sine and cosine in the matrix multiplication result them having right angles. So if you have a rotation matrix and you try to flip it upside down and around algebraically according to these numerical methods in the computer for computer graphics, if you don't just implement matrix multiplication as these even and odd sign conversions, it starts to look off, basically. But then otherwise, that's just a usual thing. And but here that the idea is that it's used for these coordinate transforms. The idea is to figure out how it's symmetric about this x equals y equals z in terms of, say, 3 functions, or if it has to be 4 or 5 or 6, or how many sides it has to have to make it so that it's a surface in that space, x, y, z space, so that it ends up being how this hyperboloid kind of works out. That the surfaces that cut x, y, or y, z, or x, z, or z, x rather, say, right hand rule, end up making it a thing, so that then the hyperbola hat can also be kind of so described. Then again, I'm kind of making this up as I go along, but all this has been around forever and it's not going anywhere. If we are interested in solutions possessing spherical symmetry, then it's into this d squared phi over dr squared plus 2 over r d phi of dr, so in second and first order in the inverse, equals 1 over c squared d squared phi over dt squared. This may be written as d squared over dr squared r phi equals 1 over c squared d squared over dt squared raw of r phi. So that has done some analysis, again, with about the algebra of differentials and the vagaries thereof, or the dangers. Leibniz's methods, of course, which are used successfully for hundreds of years before it became formally taboo, but it has to be worked out, showing that it has solutions r phi equals f of r minus ct plus g of r plus ct, constant times time. And this very much reminds of the averaging formula, because and then as well about the differences about these two arbitrary functions, f and g again being arbitrary functions. We see therefore that there are progressive type solutions, phi equals 1 over r f of r minus ct plus 1 over r g of r plus ct. Let's now return to solutions of stationary type. These may all be obtained by the method known as the separation of variables. In one dimension we have to solve d squared phi over dx squared equals 1 over c squared, d squared phi over dt squared. Let us try to find a solution of the form phi equals x of x, t of t. So this was discussed as a before, and he says to see Rutherford, and then we would talk about how this was talked about in the Fourier analysis, and also in Mogan, and also in Clairaut and D'Alembert, and also as above for the progressive, that it's about separated the terms, and that there's this idea that there's a bunch of different families of series or forms for a Fourier style analysis that arrive at coming to what's otherwise just that was the x plus y, x minus y bit. In terms of the separation of terms, that when they're equal, the x squared minus y squared equals 0, but it's that term in the middle that adds up to things. X and t being functions of x and t respectively, whose form is still to be discovered. Substituting this value of phi in the differential equation, dividing both sides by xx tt, so it's kind of like time independent, obtain 1 over x, d squared x over dx squared equals 1 over c squared t of d squared t dc squared. The left-hand side is independent of t, being only a function of x, and the right-hand side is independent of x. Since the two sides are identically equal, this implies that each is independent both of x and t and must therefore be constant. Putting this constant equal to negative p squared, dot, 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 the equations give, apart from constants, dot, dot, dot. Typical solution, therefore, is a cosine px cosine c pt, in which p is arbitrary. In this expression, we could replace either or both of the cosines by sines, and by the principle of superposition, the complete solution is the sum of any number of terms of this kind with different values of p. The constant negative p squared, which we introduced, is known as the separation constant. We were able to introduce it in the formula because the variables x and t had been completely separated from each other and were in fact on opposite sides of the equation. There was no reason why the separation constant should have had a negative value of negative p squared, except this enabled us to obtain harmonic solutions. So the opposite of harmonic is anharmonic. Anharmonic. If we had put each side of the formula equal to p squared, the solutions would have been x equals e plus minus px and t equals plus minus e to the plus minus z pt. And our complete solutions should therefore include terms of both types. The same distinction between the harmonic and exponential types of solution will occur frequently. So what I'm looking for is more than the harmonic and exponential types in some of these special non-standard functions, and about some singular families of systems that will arrive at them from kernels as of kind of this impulse from the spiral space filling and about this identity dimension kind of frequently. This method of separation of variables can be extended to any number of dimensions. So yeah, I've been looking at this for a while earlier, and it was just kind of to get into this notion again of how this is being used to figure out whether the standing or the moving for systems that rest or in uniform motion, because that's all our classical mu really has at all. And so everything else that's from this nonlinear and the non-standard and the extra classical and the potential and all this and that adds up back up to that makes it so in the middle that things are at rest in motion together is a lot framed in these. And the idea is to figure out then for these systems of that the second order displacement with respect to time is acceleration or deceleration, that it's the change from rest to velocity or velocity to rest instantaneously, and then figuring out how to come up with this in terms of what becomes the equations of the motion, all parameterized by time, how they change. He talks about two other examples of solutions in 3 dimensions, cylindrical coordinates. Talks about Bessel's equation. J sub m is finite and y sub m is infinite when r equals 0, so that we should usually require only the J sub m solutions. The idea is to figure out why that the Bessel's equation of order n with solutions J sub n and y sub m have finite and infinite ones, how that's figured out that they exchange those, and what the other side ones are that would be similar to their orbits and trajectories. Nothing ever gravitates together. Things just orbit in their trajectories each other. It's a fall gravity. So anyways, then he says one final solution is one of spherical polar coordinates. So these notions of the coordinates and the settings and the spaces and the makings of the means of the symmetries and stuff about it, a lot's going on with these symmetries. And so now when I look to reread something like Stefani's book up there on the Lie symmetries and the extended treatise on that, kind of like this book by Gonzalez Velasco on Fourier series, is all about the Fourier analysis and gets into a lot of different things. Whereas these university texts are very much just neat little tomes. They don't really do many of the developments a lot of time, but just kind of present some examples and then work them out and around and down. But still are great introductions to the things and give needed things that would be useful when you actually would have to dig out of these books how to do some things. And there's a lot to it. I'm just basically trying to skim these and arrive at something that makes it so that it's a very useful tool from the get-go and the let-out, and also particularly that it acts as a central kind of axis or singular origin for asymptotic basis, for an analytical basis for this sort of approach of the in the world of the coordinates, the dynamics of the continuous and discrete about the infinite order and finite order in terms of the classical rest of motion of the arrival at thereof. In simple terms. Bessel's equation, d squared s over dr squared plus 1 over r ds over dr, so this is familiar so far. And then this third term in s plus p squared minus n plus 1/2 squared over r squared s equals 0. And this refers then back to Incy's book, and it'll be talked about a little bit more to look back to it about why these polynomials and these functions have their values, and then also for the Fourier analysis when we've been looking at it about the periodic and so on, when in the analysis that basically the parameters let it go out to infinity, and then it's figured out what's windowed up and boxed down and vanishes out or makes for a box that happens to maintain the square, quadrature, and this halving space and the doubling space and this kind of thing. These are the dynamics. And then we get into Chladni's figures. The nodal lines are known as Chladni's, C-H-L-A-D-N-I, Chladni's figures, or Chladni's figures. A full solution of a vibrating membrane is obtained by superposing any number of these normal modes. And if nodal lines exist at all, they will not usually be of the simple patterns shown in these figures. As is the case of the rectangular membrane, so also in the case of the circular membrane, the overtones bear no simple numerical relation to the fundamental frequency, and thus the sound of a drum is not very musical. That's arguable. I mean, it can be played musically. A vibrating bell, however, is of a very similar type, but it can be shown that some of the more important overtones bear a simple numerical relation to the fundamental. This would explain the pleasant sound of a well-constructed bell. But it's a little difficult to see why the ear so readily rejects some of the other overtones whose frequencies are not simply related to the fundamental. A possible explanation is that the mode of striking may be in some degree unfavorable to these discordant frequencies. In any case, we can easily understand why a bell whose shape differs slightly from the conventional will usually sound unpleasant. All right. That's very interesting. So yeah, these this topology and ordinary differential equations and waves contains a lot in those books, and because most times you pick up wave theory from a bunch of different introductions, because whether it's used for pendular motion or periodic motion, or used for theories of periodic functions, or for lots of different things, springs, yeah, and otherwise simple systems in the kinetics and other things. It's nice to kind of have a tome where it's collected together, the theory of the parts and how that relates to the things. Because it's specialized compared to a linear analysis book. It's like, well, what am I going to use in linear analysis for? It's like, you're not going to use it. It's kind of a general course, but now let's fit you with the echelon form boots and make sure that everything is just going to be hunky-dory when you look around and find that everything can be solved with your linear analysis methods that you learn in this course after matrix multiplication and Mn, Np, and these kinds of things. And well, let's keep it square and let's keep it singular and let's keep it like this and that. And then we can talk about the adjoint Hermitian and what it means and why then it sets up for the commutative and associative and these kinds of things. Well, great, but at the same time, the applications of those things kind of get connections to the applications. Kind of like the notion of the rotation matrix, and there's special cases for right angles. They reflect sign changes instead of the usual interpretation of interpolation by multiplication, which suffices but accumulates error over time, just only because the quantities being multiplied are not infinite precision. Here, that's just kind of an example, though, is like a linear system with corrections to establish the so in the face of something that otherwise is an approximation or with an error term that has its pathological cases. That said, that's kind of a digression from otherwise just about the particular mathematical object or the wave. Has a lot going on in terms of all the continuous and discrete and the theory and the particles and the waves, and it's part of a very rich glossary of the particle zoo and the wave farm, or what you want to call it. It has these deconstructive accounts of the wavelets in accordance that for this rest and motion, for displacement and acceleration with velocity in the middle, or as for the rest and motion is displacement and velocity with acceleration on either side, that these are the things that get into beyond the perfect inelastic collision, how to explain why the ball bearing desk toy, the click-clacks, and after it starts, that it click-clacks at rest in the middle, that it ends up moving. As a sort of example, and that could be very readily explained. It's like, well, it just kind of tends to import a little bit difference or this or that, or it's like a Casimir force thing. It's like, well, you're really going to invoke the Casimir force and blow that up in terms of these phonons in the acoustic. It's like, and when it could just be as simple as if they start rubbing or something like that, It's like, well, yeah, I mean, it's possible to do so, and the idea is to figure out how it's both. Because at the end of the day, one or the other solution, classical and superclassical, doesn't suffice. Because the superclassical by itself doesn't end up being very tractable. As the classical that we've arrived at as a science and mathematics and mathematical physics is sensible, fungible, and tractable. Then it's not complete is the big key thing for foundations to accomplish, because foundations is to make for complete mathematics and complete science. So then the idea is that then for these higher order systems, it's to result as minimal models that model the most of the nonlinear and the potential theories things. And then that's what the idea is, to get that to come down from harmonic theory and the harmonic functions, to come down from the exponential and the differential and the asymptotic, all about the linear, which is where the identity dimension. It's also a straight line with slope 1, you know. That these are the kinds of things that get into for rest and 0 and velocity in 1 and all these kinds of usual centralizing uniformizing things for a continuum limits when something goes to infinity, and in the continuum limit an infinitude of infinitely small things that maintains a character, to the vanishing and attenuative, and what's the floor when everything just kind of radiates freely. These are the kinds of things that, from my perspective, have then that the most fruitful way to approach this is not necessarily with using the foundations as they are, say axiomatic set theory, because the continuum limit has to be built way on top of that, and it's too late. Something will break on the way. It has to be built in from that, this basic dichotomy there, and built out all the way. Kind of like what is the oak tree and there's the rigid tree and the flexible tree, and it's got to be both. This is how it works. Well, all right. Hey, have a great day.